Hi, I'm Ben Dozier, and this is my talk for the Nearly Carbon Neutral Geometric Topology Conference. It's a pleasure to be here on YouTube. It's always an interesting place to be. And I'd like to thank the organizers for inviting me and for putting together this novel conference. Okay, so let's get started. So I'm going to talk about translation services with multiple short saddle connections. So there are various different ways of defining a translation surface. So I'm going to say it's a collection of polygons in the complex plane with each edge identified with another edge that has equal length and that's parallel. So so one good example is the regular octagon. Bet you didn't know I could draw that good an octagon that quickly. So we take this octagon and we identify opposite sides. So this. And so what you get is, in this case, you can work out, you get a genus 2 surface topologically. So, and then there's sort of one special point on it. So all of the corners of this octagon get identified together. If you follow these identifications around, you see that. And so these all get identified to one point on this torus, and it has cone angle 6 pi. We label that as 2 because you can also think of a translation surface as a given by a Riemann surface and a holomorphic differential, and the zeros of the differential correspond to these cone points, and this is a 0 of order 2. So this this is the definition, but then there's an equivalence relation. So this is up to cut and paste. So you're allowed to take different polygon representations and cut them up into pieces and move them around and paste them together, and gives you different representations of the same translation surface. So each translation surface lives in a moduli space of translation surfaces of the same topological type, sort of with the same discrete data. So the data is the topology of the surface. So in this case, it would be a genus 2 surface, and then also the orders of the zeros of the differential. So this lies in a stratum H2. So if you just knowing the orders of the zeros actually determines the genus. Okay, so then there's this important dynamical system on the space of translation surfaces on the stratum. There's this action by SL2R. And what it does is, so you take some matrix and you apply some matrix to this surface. So we could do like the matrix 2, 0, 0, 1/2. And then what it does is you just apply the matrix to, the polygon thought of as a subset of R2. So it's just the sort of standard action of SL2R on R2. So in this case, this is what you get. So it sort of stretches in one direction and squeezes in the other direction. Okay, so then on this space of translation surfaces, there are these period coordinates. So on each stratum. And these give local coordinates, so they can be extended to a global coordinate system. And so they're modeled on the relative cohomology. So of the surface relative to the zeros, but so this set of sigma is the zeros of the differential. But sort of more concretely, what you can do is you can take like a set of independent edges of the polygon. So like for this octagon case, you choose, you know, just the four edges that that are independent, and the other ones have to kind of follow along. And you can vary those a little bit, however you like, you know, and then you get, if you vary those four and then you make the other four kind of imitate what the original four did, then you still end up with a translation surface. And this describes the whole neighborhood of your original surface. But it's only a local coordinate system because if you say you move both of these two edges so that they collide, then you kind of get a problem drawing a translation surface. So they don't give you, you're only allowed to move a little bit. Okay, so then so we want to do ergodic theory. So we need a natural measure, and actually we're going to look at lots of different measures, but so there's this canonical measure called the Maser-Riesch measure, and what it is on a stratum, and what it is so mu mv on H it's just locally Lebesgue measure, linear Lebesgue measure in period coordinates. So like in the case of the octagon, you just would have these four independent sides, which would be four complex numbers. So you could think of it as a point in C4 or a point in R8, and then it would just be a Lebesgue measure in R8 locally anyways. But then it has interesting global properties that one can investigate. So this is a measure on the whole stratum. Oftentimes we want to look at mu mv on the unit area locus. So this is going to be defined as, so it's just all surfaces in the stratum that have area 1. So there's a process for getting from the Maser-Riesch measure on all of H to get a measure on H1. So the properties of mu mv on H1 are that it's SL2R invariant, and also SL2R preserves the unit area locus, right? Because SL2R preserves area, and it preserves this measure, and that's basically just because it's SL2R acts linearly, and this is a linear measure. And then a deeper fact is that the total mass of H1 with respect to the Maser-Riesch measure is finite. So you could, for instance, normalize it to make it a probability measure, but yeah, the total mass is also an interesting thing. So sometimes you don't want to do that. For this talk, it doesn't matter so much. But and then the third thing is that it's ergodic with respect to the SL2R action. So these are quite nice properties, and they put you in good shape to do ergodic theory. And then there's a general principle, which is that so to understand, so the invariant measures, like not just that Maser-Riesch measure, but understanding all invariant measures for the SL2R action, these measures govern the SL2R dynamics. So if you want to understand this SL2R dynamics for completely, you should understand all the invariant measures. So so how do you go about studying all the invariant measures? Well, I mean, a priori, if you didn't know anything, you might think the measures could be kind of crazy things. Maybe their supports are kind of fractal subsets, but it turns out that these measures are all fairly nice. So there's this landmark theorem Eskin-Mirzakhani, which says that any mu satisfying the properties 1, 2, 3 above, SL2R invariant, finite, and ergodic, is what's called affine. Which you can think of as kind of specific type of nice. So it's supported on what's called an affine invariant manifold. It's actually an orbifold, but this is the notation that's standard. And what is this? So it's a submanifold or suborbifold of the stratum that's locally cut out by linear equations in period coordinates. So period coordinates give the stratum a local linear structure, and these are just sort of locally, the affine invariant manifolds are locally linear subspaces with respect to that linear structure. Now, so that's what the support is, and then the measure is locally, it's Lebesgue measure on this on the subspace corresponding to M. So an example of such an affine measure, well, the Maser-Riesch measure is an example, but here's a another type of example. So you can look at what's called the E4 eigenform locus. I'm not going to talk about why it's called that, but the one description of it is you take surfaces which are built out of, so two tori. So you have these two things that are each, so each of these is a torus. And then, so you glue them together, so there's this kind of connect sum operation you can do. So you can make this little slit in both of them, the same length and parallel, and then you can identify the left-hand side of the slit on the left torus with the right-hand side of the slit on the other torus, and then opposite here. So which means that if you come in from the right here, you hit A, and then you get glued over here, so you move into the other torus. So it's drawing these two things together. So so the eigenform locus. So there's, you know, you can, so if we were thinking about period coordinates, we'd have there would be 5 of them. So there would be like A and B here, and then the other two sides of the torus are determined, and then similarly like A prime, B prime here, and then you'd also have a period coordinate for the slit, which has to be the same on the two sides because you have to be able to glue them together. So the E4 is where, so it's the locus in the stratum where A is equal to A prime and B is equal to B prime. So in other words, the two tori are actually identical tori that are glued together. So the coordinates then on so these are linear equations. So this E4 defines an affine invariant manifold. These are two linear. They also have to be homogeneous and with real coefficients, and these qualify. So then the measure is Lebesgue measure in the coordinates. So this mu E4 is this affine measure, and it's Lebesgue measure in the coordinates A, B, and C. So in other words, it's locally Lebesgue on the subspace corresponding to M. Okay, so there's there's quite a few known examples of these affine measures, but it's still a very important open question to classify all of them. And this has relations to homogeneous dynamics. I mean, there's an analogy with homogeneous dynamics where the corresponding theorem would be Ratner's theorem, but we're not quite at the level of Ratner's theorem in, for the SL2 action on strata, because we don't actually, we know this nice theorem that they're affine, but we don't have an actual classification. We can't write like a list of all the affine measures. Okay, so that's an important problem. I'm going to talk about something a little bit different, which is how does mu relate to the geometry of the underlying surfaces? So mu is this affine measure. So more specifically, I want to think about what the measure, the mu measure of the epsilon thin part of the stratum. The epsilon thin part is the locus where surfaces in stratum that have has a saddle connection of length less than or equal to epsilon. Okay, so what is a saddle connection? I haven't defined that yet. So if we go up here to the picture, so a saddle connection is it's a geodesic segment that joins two cone points, and it could be the same cone point to itself. So for an example would be like this thing here. So you go over here, but then of course you get identified down down here, and then you keep on going up here. So so these are sort of natural trajectories, special trajectories that we want to study, and they have a lot to do with sort of the compactness and of the stratum. So this is the sort of, so to generate a translation surface, you have to make a saddle connection short. So there's a theorem. The right color. So there's a theorem of Mazur and Smiley in the early 90s, which says that so for the Mazur-Veach measure, it's just about the Mazur-Veach measure. If you look at the measure of L epsilon, it's big O of epsilon squared. So there's some constant that just depends on the stratum that you're in, such that the measure is less than that constant times epsilon squared. And the reason for the epsilon squared, just to give you some sense, is that, so if you have an epsilon short saddle connection, that's what this L epsilon is, you can think of its length and direction, and that gives you can think of that as like a vector. And so, if it's epsilon short, that means the length of the vector is less than epsilon, so it lives in this ball of radius epsilon. And then the Lebesgue measure of a ball of radius epsilon in R2 is just pi epsilon squared. So somehow the contribution to the measure from this one short saddle connection is like pi epsilon squared, and then you have to worry about all the other ones, all the other saddle connections. But it turns out that the most important term is coming from the short saddle connection. Okay, so then so that's for the Mazur-Veach measure, but then you can also get the same result for any affine measure using something called the Siegel-Veitch formula. This implies that mu L epsilon is big O of epsilon. Let's make that in particular. It's the same big O of epsilon squared for any affine mu. So that's fairly well understood when you so the case of having a short saddle connection. But what I want to really focus on is so what happens with if you have more short saddle connections. So what's the deal when you have multiple short saddle connections? So we have to define some locus again. So we have L epsilon 1, epsilon 2. I'm just going to talk about the case of two short saddle connections, so you can do things for more. So this is the locus in a stratum where there's a so X has two saddle connections, S1 and S2, and we're going to say they also have to be kind of independent in some sense. So one thing you can say is that they're non-parallel. And the length of S1 is less than epsilon 1, and the length of S2 is less than epsilon 2. Less or equal to, so it doesn't really matter. So Mazur-Smiley also proved in the same paper a result about this locus in terms of its Mazur-Veitch measure. So they proved that L epsilon 1, L epsilon 2, the volume of that is big O of epsilon 1 squared. So you get one factor of epsilon 1 squared, and then also a factor of epsilon 2 squared. So it goes, point is that it's smaller. So this is sort of a, it's more degenerate, these translation surfaces. They have two sort of independent short things. So they have kind of two places where they're degenerating, and then the volume of that is smaller. So you have an extra factor of this epsilon 2 squared. And it's the same sort of general idea that you have these two independent saddle connections, and each sort of, you get a factor of epsilon 1 or epsilon 2 squared from each of those. Okay, so then the theorem that I proved is generalizing this to any measure. So mu of L epsilon 1, epsilon 2 is big O of epsilon 1 squared, epsilon 2 squared for any mu affine. So there's a version for, this is the version for two short saddle connections. There's another version for any number of short saddle connections that you want to control. So you have to say something about sort of them being independent in the affine invariant manifold, and it's not enough just to say that they're not mutually parallel anymore. So it's a little bit more complicated to state, but it's the same type of result. So there's some previous work on this. So Avila-Matheus-Yoccoz proved a result for all measures, but it's not quite as good as this natural bound that I proved. So they proved something a bit better than just the epsilon 1 squared that you get from having one short saddle connection, but not as good as this, which is what you expect. Dugman-Wynn proved this natural asymptotic, but for a limited class of affine measures, those coming from rank 1 affine invariant manifolds, which are an important class, but there are examples known of higher rank non-trivial, so non-trivial examples of higher rank affine invariant manifolds. Okay, so why should you care about this? So there's one direct application that I know of. Gaudre proved that he proved a result on excursions of random Teichmuller geodesics in moduli space of Riemann surfaces. So excursions into the cusp of the, or into the non-compact part of moduli space. And this was, his result was conditional, or some of his results are conditional on this result that I proved, which, so this, we call this strong regularity. He also calls it that, I think. So he proved results on excursions conditional on this, so now they're theorems. So another reason to care about it is that it's a good test of our understanding of sort of more complicated degenerations of affine invariant manifolds. So sort of what the behavior of affine invariant manifolds at infinity is. Okay, so I'm going to talk about the proof in the second video, but just to give you a sense, so the tools used in the proof are the multi-scale compactification. So this is what it's called. So there are various different compactifications of strata, and this is a fancy new one due to Bainbridge, Chen, Gendron, Khrushchevsky, and Muller. So that's one key tool, and then another key tool is Simeon Phillips' algebraicity result that says that affine invariant manifolds are in fact algebraic subvarieties of strata. Okay, well, thanks for listening, and if you want to know more, there's a second video about the details. I'll give a sketch of the proof.